So we so we will talk about the epipolar geometry. This will be the last class, basically last lecture, um, and this is continuing what we discussed last time. So we look at the camera model, and then is the camera model is needed. Like if we would like to kind of extract, relate 2D and 3D, 3D and 2D information. Like if you want to know how's the 3D point in space will be mapped into the camera in the 2D space, and kind of of course from 3D to 2D you will lose information. You know from 3D to 2D, but in general you cannot from 2D to 3D. But if you have multiple cameras, then just using trigonometry is possible to just if you know the corresponding point from one scene to another scene, then it's possible you can predict the 3D the depth of that point as well. So combining that you can get the exact 3D information. And we like to talk about this epipolar geometry, as you will see later on why it's needed for kind of effective reconstruction. So this is just an illustration that I guess many of you talk about in your presentation, structure of motion. And okay, I'll just skip those slides here. So now let's get to the something very simple first. Consider we have two view here. So and for two view, let's say F is as the focal point of this view here, and you can see this is the disparity here. This camera setup is completely aligned, and for this particular setup, we can very easily to find the connection of this the depth of this point from the disparity information here. So namely for example this is the left view here. Let's say the disparity is XL, and the right view here, this is XR here. So actually I say disparity, but more meaning that the point here, you can see is XL from the origin here. For this left scene here is XR to the left, from the origin here for the same point here. So then we can use, you see these two red triangle and the blue triangle are similar. So therefore we have this T plus XL minus XL, or that's or actually this is a typo here, should be minus plus XL minus XL is over Z over C minus F. That's this length here should be equal to T over C here. So anyway, using this simple trigonometry, you see C, the depth here for this point is just proportional to the disparity. Basically is proportional to how the disparity here is XL minus XL here. So you can imagine if the disparity is higher, then the object should be closer, and if disparity is smaller, then the object is farther away. So this is pretty simple scenarios that you have these two cameras completely aligned this way. But in general, you don't have camera calibrated like this, and you typically will have just two. Let me go to a scene. I don't have a scene, but in general, you may have cameras may be tilted, right? So I have a view is looking like that, and a view looking like the other way. So and of course if you know this camera information, basically the camera parameters that we described last time, then you should be still able to figure that out, what will be the corresponding 3D points from the corresponding locations in the two views here. But one thing like is important. Let me just go uh, directly that like to, for example, if I want to reconstruct the entire 3D scene here, I want to know like for each of the points, like what's the depth here. So what I need to know is I need to find the corresponding points for, let's say, like this patch here should be correspond to the patch here, and this patch correspond to this patch here. And of course, like for the smooth region, it becomes difficult. But assuming even I can do that, but for looking for finding this correspondence in general, without any additional information, for this point here, I need to find the corresponding points in the entire scene here for the white image, and so on for every point here. So what you will see later on in the what we discuss in this epipolar geometry is that like if we know the if we know epipolar geometry and we know some of these parameters, underlying parameters of your camera, then you don't need to look for the entire space for a corresponding point. For example, for this point here, actually I will know like on the white image here, it will only fall into some line here. This will be like known as an epipolar line. So therefore, instead of trying to look for corresponding point in the entire image, for each of this point here, I will just look for like on a single line. So this not only like reduce the complexity significantly. Okay, I can skip this now. So this is precisely illustrating this. So if I have point here, like let's say this is the point in space here. So let's say in the left image, I see this one, I know this point is here. So of course, I just knowing the point is here in general, I cannot find the 3D location here because this point just from the left image here can be like originated from any points lie on this line here, right? But if I also know some information on this right image here, so say if I know that I see it here, then I know the point in space is actually here. And also you see that like if I know like in the left image is at this point here, we don't actually need to look for the entire scene for that point. And as you can see, like this point here should only fall on this line here because it can only fall on this line, so therefore should only fall on this line here. So therefore we can just look for the points on this line here. So this is the main idea for epipolar geometry, and we'll go into more detail like immediately afterward. So but you can see that that's the power here, like it not only like reduce the complexity significantly looking for the corresponding point, but also like it increase the accuracy a lot also, because like there can be like for if I don't search for this line here, then maybe like have points like somewhere out there also like pretty similar to the patch here. So but just from the geometry here we can exclude this one, so we can reduce the potential errors, chance of having errors much more, a lot more. So and here is some terminology for the epipolar geometry. We have this O here, so it's like the camera center from the left view and the right view here, and then like the line in space connecting the two camera centers known as the baseline. And the baseline actually will kind of go through this image plane here of the virtual image plane for the left camera and right camera, and the point it go through that one is looked at is called the epipose. So we have this left epipose and the right epipose here. So and then like and then if I have considered the point here, like let's say this the target point here, this target point along with the two camera center will form this epipolar plane, and the epipolar plane will intersect these epipolar lines. So this that we mentioned earlier. So here just some more illustration. I have like this like say this is like some target points, and this is a different epipole here and different camera. So like this is a setup that like you can see like that will be an epipole, but like the epipole is like the camera like size. I mean the camera's sensor size is not big enough. The view is not big enough, and the epipole, like for example, for the left image, should converge like very far away outside the boundary of this view here, and so on. Like for the this image on the right, also the epipole. Like actually, if you continue to draw this line here, it should converge somewhere very far away. So this is like a setup we have like earlier. So I hear something like any questions. So and so this is another possible setup. This is like the setup we have like at the beginning. So we have the two view here, two cameras exactly parallel, like shooting like directly to the front, and they kind of like the two camera align in parallel, and you can see like in this case, the two camera center won't kind of intersect with like if the baseline that connecting the two camera centers will not intersect this image plane here. So therefore, like there will be no epipole here, or like you can imagine the epipole is like at infinity basically. So you see like this line here, this epipolar line here is actually kind of in parallel with each other. And this is like another view that like here basically you have like two cameras, one is in front and the other like is at the back. So then if you draw the baseline, the epipolar line, the baseline kind of like intersect about in the middle of like the two views here. So as illustrated like this one here. So therefore you can see the epipole is like somewhere here, right? So you see the epipole like in the middle of the image in the two views here. So now actually I'm thinking like maybe I use a whiteboard. I guess maybe it's easier to discuss something like that. Like so let me share a whiteboard. I guess I should. Oh, where's my? Okay, let me make myself host. So where's my other kind? So we have, as we said, like what we have is something like that. We have two camera view here, right? And we have like this is camera center, and it's going when they connect to each other. There's a baseline here, and hitting this epipole. And let's say this is like some target point here I'm looking at, and then I have this center here, and this camera point will correspond to some point here. Let's say, and the camera point will correspond to some points here. And now what we are going to do is let's say I call this center on the, let's say this center on the left. Maybe okay, my slide is use O pi. Maybe I use O pi also, and this is a O, and then like now like I have basically the two cameras can have like two different coordinate system, right? So on the left camera, let's say I have a coordinate systems that correspond to the location. I call it XL. This is the coordinate of the points here that according to the left camera. And let's say XL is the coordinate of the point correspond to the right camera here. So note that this 2 is the same point, right? But just because the two cameras have two coordinate systems, so therefore the coordinates are different. And let's say this point here projected to this plane here is XL hat, small XL hat here, and this point, this one here coordinate projected to the right camera is let's say XL hat here, let's say. And we have epipolar line, let's say this is L and this is L pi here, just according to my node. And okay, let's write so much so far. Now first thing I want to kind of relate the coordinates of this with this one here, like the left coordinate with the right coordinate. So what should I do? Let's say for the camera center here, I translate the camera center with from the left center to from the right center to the left center. The translation vector is let's say t. That means that t is let's say o pi o. Let's say this is the vector o pi o here. That's t. And let's say and because the camera, as you can see, I'm shooting in this direction here. This is shooting this direction. Apparently, there's some rotation here. The coordinate system for the for the right camera and the left camera should not be the same. And let's say I need some rotation to rotate from the right coordinate system to the left coordinate system, and let's say this is R here. So if I have that, then I can transform, I can equate XL and XL this way. So XL will be basically equal to, XL should be equal to XL minus T, right? Because I have XL here is this, maybe I'll use another color. XL here, this is XL here, is something equal to this XL here minus T, right? Minus T will be like that, right? So XL is basically equal to this minus T plus XL, right? So, but this is not that yet. I cannot just say XL is equal to X. This is not correct. This is not right. Because remember that, okay, this may be confusing. If you look at that, look like, yeah, XL of course is just equal to XL minus T, but it's not right, because remember that this is also XL and XL at coordinates according to different coordinate systems, that basically the axes for these coordinate systems are not the same. So for XL here, for example, I have a coordinate system maybe like this. This is a x axis, y axis, and c axis here. And on the right, my XL can be like this, right? I have x, y, and c here, something like that. So to equate them, I should use this rotation, right? So actually, my XL therefore should be after I have this vector like that, I should just rotate the coordinate system, right? I should rotate the coordinate system. So I will have XL is equal to R multiplied by XL minus T here. So is that clear? So what we are interested in is we want to create a matrix that's known as this essential matrix. Maybe I should stop writing here. Essential matrix the essential matrix have a property like this. So this E, if I consider the coordinate, so from the left camera it's like XL, as I said, like XL here, and the coordinates in the y is XL here. I will have like this, like for all points that based on like, by the way, I need to emphasize this is a 3D Cartesian. Okay, I made a mistake last time. I keep saying Euclidean coordinate system. What I mean is a Cartesian coordinate system. Cartesian, I'm not sure how to spell that. This is like 3D Cartesian again. So it's 3D Cartesian, so therefore both vectors is should be have length 3 here, right? So what I mean, like in this scene here, as long as like we are referring to the same point here, the left in the left coordinate, I mean the coordinate system from the left camera, XL multiplied by this E and multiplied by this XL will be equal to 0. And I want to look for a matrix like that, and this is known as the essential matrix. I mean, so actually this is a funny history, a kind of interesting history. By the way, if you know deep learning, like Jeffrey Hinton is like the kind of like regarded as the father of this deep learning, right? Actually, this is invented by his advisor, like this essential matrix, and even more interesting is that his advisor is not, of course, it's hard to say who should study computer vision at that time. He is not something like an engineer or a computer scientist. He's actually a neuroscientist, something like that. Okay, so now I want to say that what will be this essential matrix. It turns out that like my essential matrix is very simple. It's just have a form like this. My E that satisfies this condition is just equal to R times Tx here. Now I need to elaborate what I mean by this Tx here. This is a matrix that corresponds to a cross product operation. What I mean is that like if you think of matrix, think of like cross product. I hope you still remember what cross product is like. If I have two vectors like in 3D space, let's say I have a T here, cross with a vector X here, let's say. So what is that? So it can be represented by something like that, right? Let's use the IJK notation for that. I guess this is the easiest to remember. So it's like, let's say this is T1, T2, T3. So T is like a three-dimensional vector, right? T2, T3, and so on. X is like X1, X2, X3. Now, maybe I also write it down. X is equal to X1, X2, X3 here. So I have something like that, right? So, and what it means is that like this T multiplied by X is like also a vector, and actually maybe I can write it also in this column form here. That will be like determinant. So it's T2 X3 minus T3 X2, and this one is minus T1 X3 plus T3 X1, and K is like T1 X2 minus T2 X1, right? So this is actually T multiplied by X here, the cross product. And we also, like, you remember the cross product, the property is something like that. If you have cross, like this is like, for example, X. So you can also show that what is the cross product, kind of like in terms of geometry wise. So the cross product is like if I have a vector like that cross with that, then it will be like in the direction with this right hand rule here. I think you learned it in EM, and so this vector will be perpendicular to the plane spanning by T and X, and so therefore like when T and X is actually let me also say like if the angle between T and X is theta, this vector here will be like the magnitude of T multiplied by magnitude of X times sine theta. I mean the magnitude of that vector. And so therefore like you see if like T and X are parallel, then like T t cos x is equal to 0. And okay, and let's go back to here. So I have t multiplied x is equal to this guy here, and I can write it in the form that like this is like x1, x2, x3 multiplied by some matrix, right? The matrix will be what? It will be like 0, wait a sec, yes, 0 minus t3, t2, right? So you see the first row here, if I have like minus t2, minus t3, t2 here, minus t3 multiplied by x2, so I get this term here, minus t2 multiplied by x3, I get this term here. So similarly, I have like this second one is like t3 0 minus t1, right? Yes. And then this one is like minus t2 t3 0, something like this, right? So, and we can call this matrix like tx here, something like t multiply here, I shouldn't say x here, t product here, and then we will just define this as like this t product matrix, and if we go back here, what I mean is that the essential matrix is actually just given by this guy here. So let's see why this is true. So we want the essential matrix to have this property, right? Basically, we want to have this property here, and let's say if I have, let's say this point here, let's say consider the same point here, xl and x, this point here, x here, that on the left wheel is xl, right wheel is xl, then I have xl transpose times e, that's e is like rtx here, let's say, times xl, right? Now I can substitute what we have with xl here. We say that xl is equal to this guy here, right? So therefore this one is equal to xl minus t transpose r transpose, right? Because like ab transpose is equal to b transpose a transpose, something like that, right? Multiplied by r, multiplied by tx, multiplied by xr, and R is a rotation matrix, right? So because it's a rotation matrix, R transpose is equal to identity. This is just identity. That's property of rotation, because for rotation matrix, R transpose is like rotate back basically. So R transpose R will be just equal to identity. Now then Tx times XR will be just like equal to T cos XR, right? And then like this XR times T here, actually transpose times this guy here, is really like a dot product or inner product of XR something really like this, right? So it's like an inner product of, or maybe I keep the same notation, do not use the inner product, but let's just do that, then XR minus T transpose, just do that. But then this we can split the terms, that will be XR transpose T times XR. I'm sorry about that, like it may look confusing. This is time, this is cross product. Yeah, maybe I use my another writing for x. XR, x, XR. Minus, I don't need this bracket here, minus T transpose T multiplied with XR, right? And so then this is basically, as we mentioned, if like T multiplied by XR, that would be like in the direction like perpendicular to T and perpendicular to XR, right? And this is like the inner product of like, so what I mean is like T times okay, so therefore like this will be perpendicular to XR, right? So for inner product, if like you have like two factors are perpendicular to each other, the inner product will be just equal to 0, right? So therefore this is equal to 0, and for the same reason this is equal to 0 as well. So therefore this is just equal to 0. So we have, this is the essential matrix that we show that this is like have what we want here. So let's also look at one more property for this essential matrix. Let me erase something, maybe I erase here. So let's say I have some point here in the middle of the baseline. Let me call it like x naught here. And for the x naught, let's say I carve like, so this x naught of course like will correspond to point on this epipolar point here, right? This x naught actually will map to this epipolar here. And let's call this epipolar on the left like sorry, this is on the right ER, and on the left EL here. And then like and also okay, for the coordinates, this is like after the projection, right? On the screen you see like ER and EL, but the point in space will be, let's say, equal to x r naught in terms of the right camera perspective, and let's say it's XL naught for the left camera perspective. So what we want to show next is like that we'll use later on is like E times this essential matrix E times XR naught is equal to 0 as well. And also like we will have like E transpose XL naught is also equal to 0. So I'll just show one of them. The other is actually the same, like very similar. So let's say for this guy here, we have this E is equal to R times Tx, right? So ER times Tx times XR naught, that one. So therefore what? This will be equal to IR times T multiplied by X. Again, I try to XR naught here. Right. Now I argue that this will be equal to 0. Why? Because like, think of what is T here. T is like basically this vector here, right? T is equal to vector from, is equal to O pi O. It's like the vector from here to here. And this is like according to the right camera perspective. And X R naught here is also like kind of like same direction of the vector. Note that I need to make sure they are from the same camera perspective. If they are from a different camera perspective, that won't be true. For example, like I shouldn't have R times X L naught. This is should be equal to 0. So but this is equal to 0 because they are from the same camera perspective and they are also parallel. So therefore, like as I mentioned, like cross product like of like two parallel vectors is just equal to 0. So therefore, this is equal to 0. So that's equal to 0. So you can show something similar for this guy here, but I will just I'll just omit this here. It's like you may try that out like as exercise if you're interested. So actually it's like in the slides anyway. If you yeah. So we have this property here and also this property here for the essential matrix. Now I want to introduce this known as fundamental matrix. Maybe I can erase this one now. This is a proof for this. Yeah, but yeah. So remember what we have here so far. We have this is the essential matrix, right? We have this property. It's very handy. This is like the basic property, like relating these points in space from the two camera perspectives, like for the same point from the right view and from the left view. And we show that for essential matrix from the pool perspectives, like XR and XL, they're related this way. But note that like all these are Cartesian coordinate in 3D. Now we want to consider like the points projected to space. So we want to connect like this this XR hat XL hat somehow instead. Actually, I should put like XL on this order. Again, XL hat and XL hat instead. So again, like XL hat and XL hat is basically the point that projected to the space, projected to the cameras here, actually to actual screen here. And again, and also like be careful, like for here XL and XL, I'll use a different coordinate system. I'll use this homogeneous coordinate system. What I mean is that my XL here is actually, for example, this XL here is a XL1, let's say, XL2 and 1, something like that. This is a scalar value here. This is the vector here. XL is a vector here. This is the scalar value here. And so as like XL will be like this. And we want to show that like we want to find another matrix like known as the fundamental matrix. This is like fundamental have a similar property as a essential matrix. The fundamental matrix gives them this F here, XL hat transpose multiplied by F multiplied by XL hat is equal to 0. Oh, by the way, like, do you guys have any questions so far? Like, do I need to clarify anything? You're good? Like, everyone's good? It's complete silence, so I don't know. Okay, anyway, so let me continue then. So, and it turns out that like, okay, and I will show that what will be this fundamental matrix. First thing first, I need to recall a little bit the camera matrix we have last time. Remember that the camera matrix have some extrinsic part and intrinsic parts. Basically, the extrinsic parts is like some RT. Hopefully this is correct. RT and multiplied by a K matrix here. So the okay, maybe I don't want to go. Let me wait a second. Probably should check, make sure that I. Yeah, let me just copy here. The K here will be something like, if you remember some D scale, I just use the same exact rotation here, DI minus alpha DI, actually some U0, V0, 1 here. So the detail here, it doesn't matter, I just call this K here. But this is the extrinsic part, sorry, this is the intrinsic part, and this is the extrinsic part. And remember that like this is for homogeneous coordinate, so for some point here, x, y, z, 1, from 3D space map into 2D space, like let's say x, y, 1 times some scaling here. So will be related that way. So in the nodes I use scaling u here. So use w, and let's use w again. So now for the camera, remember what's this extrinsic matrix here? Extrinsic matrix correspond to the world coordinate, how the world coordinate related to your camera coordinate, and in my case here, for each one of my camera, my world coordinate is actually exactly equal to the camera coordinate. So therefore, like in this case here, this R and T is just identity and 0. So therefore, it's just equal identity and 0 here. So this is basically this thing is gone, the extrinsic matrix. And then you see like from the homogeneous coordinates here in the 3D space to the screen in the 2D space is just equal to multiply by the k alone, really. And also, like if you see, like because I have a 0 here, right? So this last one here doesn't do anything now. So I can really, so in this special case, when this extrinsic matrix is gone, I really have the mapping is just reduced to something like that. X, y, z times this k is equal to my coordinate. Maybe I use hat here also, like just to match my rotation in here. It's just equal to this. So with this, then you see that I can very easy to show that like my fundamental matrix, if I choose it to be like E times, let's say, KL inverse on the right hand side and times KL transpose inverse on the left hand side, I will be able easily show that this property that I want will satisfy. Here the KR and KL basically is the intrinsic camera matrix for the left camera and for the right camera. So let's just quickly show this. So say like if I have f is equal to this one here, so therefore like I have like XL, keep forgetting I should write XL like this, XL hat transpose times KL transpose inverse E KL inverse times XR hat. Okay, for this guy here, like XR, I can write, as you can see here, like now XL here is actually equal to okay, XL hat here is actually equal to KL times XL, right? So in Cartesian coordinate, 3D Cartesian coordinate multiplied by the camera matrix, intrinsic camera matrix should give me this homogeneous coordinate in the screen for the left hand side. So then this, therefore like I substitute this into this one. So do the transpose, and I have XL transpose. Like this should give me XL transpose KL transpose and KL transpose inverse E KL inverse. And also I can do the same thing for XR, right? So XR should be equal to KR times like XR, something like that. So then the KR and KL will be cancelled, right? So both ends are cancelled. Then I will go back to this one here. I can go back to this one. This one is actually equal to 0 here from my equation for the essential matrix. And actually, so maybe I erase this now. So I have basically, so that if like my f is equal to this guy here, then this will hold. And similarly, I will have property like, let's say ER, again it's like the epipolar location on the right view there, let's say ER, and in homogeneous coordinate, and ER, f times ER will be equal to 0, and also like we'll have like f transpose times EL, basically is the epipolar on the left hand side here, will also be equal to 0. Again, like this is very easy to show. So like for example, I just show one of these here, like f here, again like f is equal to this guy here, right? So therefore it's equal to KL transpose inverse times E times KL inverse times EL, and EL now therefore is equal to x naught is equal to EL is actually equal to KL times x naught, right? Something like, so therefore it's like KL transpose inverse E KL inverse KL times x naught. So KL got cancelled, and again like we have this property earlier on, that's E times XL, XL naught is equal to 0, so therefore like this is equal to 0, so therefore it's equal to 0. And you can do the same thing like for F transpose also. So now we have several of these property. Now we introduce this essential matrix and fundamental matrix. You may still say, okay, why we have all this? What's the point for that? So it's coming up immediately now. So we have gathered like several properties here. Maybe I use a red again. So we have these two properties here, these properties here. Again, like for the fundamental matrix, these XL and X naught are actual points that you see in the space. So you see the points in the space, but it's in homogeneous coordinate, but it's still like the location of the points in not in space, in the screen, on the screen. I'm sorry about it. It's a point location, actual location points in the screen. And now like, okay, need to digress very quickly. So consider a line here, for example, like a line equation. For example, if I have some line, I need to describe a line. So I need this because I need to some representation to represent this epipolar line here. So if I want to say like, remember our goal again is like, if I know the one point, like for example, if I know a point like on the left screen here, say I see it at this XR hat here, I want to know like the corresponding point like on the right screen. Like I don't want to search the entire screen. I know that it will align on the epipolar line, but I need to know where is the epipolar line. So therefore I need to digress a little bit to have a way to describe a line. So of course we can describe a line using a linear equation, like, okay. So this is a line basically, right? So this is a line, but you can think of it differently. So I can rewrite this as a ABC a vector multiplied by xy1, right? So this is equal to 0. So therefore you see for a line, it's really, and I could use this as a representation. This is I call this L, something like, or like maybe I call this L transpose, just make everything a column vector. So then you see that like for a line, if I represent a line with L here, then the inner product of like L, basically L transpose times a point in the homogeneous coordinate, because this is essentially a point representation of x and y in homogeneous coordinate, right, is equal to 0. So this is a very kind of cool representation, right? So basically, if you think of like three numbers that represent a line, then a point on a line a point will be on a line if and only if like the points in the homogeneous coordinate multiplied by L, I mean the inner product of them, should be equal to 0. Now let's look at like what we have earlier here. So if we look at like what we have here, like in the fundamental matrix, you see like because we say if we have somehow have a point here in homogeneous coordinate, this is a xr hat here, something multiplied by that is equal to 0, I mean the inner product of this guy is equal to 0, then this one is essentially represent a line that this xr hat fall onto. So therefore I can think of like this is actually a line, right? I can think of like xl transpose f is actually a line. So this is a line representation because you multiply out this give you 3 numbers, right? And these 3 numbers is basically this ABC here. And I have basically this line, this point here will be on this line, right? So actually this is my epipolar line. This is my epipolar line for this. Okay, I know this is a kind of small here again. So I have this point here, xr hat. I'm given this point xr hat here on the white screen here, and I'm interested to find the epipolar line, and the epipolar line is actually this line here is just equal to this. Oh, okay. I'm sorry. I messed up. Let me go back. Should be this way around. So I'm giving a point like xl hat here on the left screen. Let's say left screen. I know that this is L hat here, and I want to know the epipolar. Shoot, okay, this actually I was right at the beginning that that's let's see, I use this representation, right? This is a XL. Oh, yes, here is okay. It's right. So I have the left side. Okay, sorry about that. Like, okay, let me make sure this time is right. So I have the left side here. I see a point. Let's say I have points here. I know the points here is XL. Here. Now I want to know on the other screen here, like where is my point, right? And I want to find the epipolar line on the other screen here. And I'm saying that at the other screen, the epipolar line here is just equal to the this line here is just equal to XL hat transpose. So or like actually it's just equal to F transpose times XL hat. And because you see that like this thing here, I can really write as like F transpose times XL hat transpose times XL hat, right? And you see that like for this line here, this line will I mean XL hat here will fall on this line because of this equation here, because XL hat times this line equation times this L here will be equal to 0 as given by the fundamental matrix. And by the same reasons, we can do the other way around. If we start with like XL hat here, we will know like where is the epipolar line for this guy here. The epipolar line is actually just F times XL hat there. So with F times XL hat on the other screen, just look at for this line here, you can find this XL here. So and yeah, that's basically it. And yeah, let me just switch back to I want to share my screen again. I'm looking for my. Maybe I need to just here stop sharing first. Okay. So actually, this is like basically everything like on the slides here, and if you wait, there's something weird for this. So as we mentioned, like this fundamental matrix and yeah, I guess this slide kind of summarize again. So we have like for if we have a point on the so if we start with like two scenes here, like for example, like so we know the fundamental matrix here, like F that is given earlier, that is like related to the essential matrix, basically K. Maybe I write it down here again. So this fundamental matrix, I don't know why it doesn't switch to. Okay, so fundamental matrix that is given by K KL transpose inverse multiplied by K inverse, something like that. This is a little bit hard to read, but the E here is equal to just the rotation times T x here. So this is like the T, and the rotation is the rotating the camera coordinate from the left hand side, from the right hand side to the left hand side. And we show all this, we show all this, and basically to use that, as you see, if I know the fundamental matrix eventually, then for example, if I have a point like on the left, so if I actually, yeah, this illustration have a little bit problem, so maybe I just, so if for example, if I know a point on the right here, then my epipolar line on the left will be just equal to F times XR hat here, so we'll get this point here, and we know that like just look for the corresponding points just on this line. And similarly, if I have a point on the left camera XL hat here, so I know the epipolar line on the right is just F transpose times this XL hat. So if to find the corresponding point, we just need to find on this line here. So and then like okay, the remaining quick things to mention is like, okay, we need to find this fundamental matrix, right? So again, this is very similar to what we did in the past, like in the last lecture, and also like in trying to look for homography. So basically, again, if you start with knowing some corresponding points, like in the two scenes there, like for example, I can use 8 points, like the actual minimum you may use 7 points, but 8 points is more stable. So you can use 8 points, and for each point here, because like the fundamental matrix will satisfy this equation, right? So let's say I can write the matrix is like F1 1 1 F1 2 F1 3 F2 1 and so on, and then multiplies on the left hand side this maybe I use x pi here, like just as this line here, and then like x1, x2, x3. So when you multiply out, you get this equation here, right? Oh, okay, this x here is a u. It use yeah. Oh, sorry, it's actually not x. It's just actually it's just homogeneous coordinates. I only have like two elements, two non-trivial elements here. It's just u pi, v pi, and 1, and this is just u, v, and 1 here. So if I expand that, I will have this one equation here. So if I collect enough equation, again, I will have a system of equations. Again, I will be able to solve f. So just like last time, we can use SVD, and we want to make it small, so we just look for the minimum like single value, and then like the corresponding like single vector will give you the f there. One last thing is like, know that like the fundamental matrix is actually have a rank less than it's not full rank, it's like it has only rank equal to 2, because if you look at like what's fundamental matrix, I think I still have to the fundamental matrix is equal to something multiplied by E, right? And E is equal to rotation times Tx here. And you can easily verify this Tx itself is not full rank, only have like at least at most rank equal to 2, so therefore like the whole thing f will not have full rank. So as you see, like if you try to estimate the fundamental matrix, if you don't force it to be full rank, you may have like the epipolar doesn't converge to one point in the scene. So, but you can easily fix that, like just do SVD again, just do some SVD trick again. So it's like have a low rank approximation of a matrix. So I guess I will, okay, I have some time here, I guess it's okay I mentioned this. So it's basically like if you use single value decomposition, this USV is essentially you are just doing, I mean this is so okay, and share whiteboard again. So let's say USV, if I have a matrix like SVD to kind of decompose that, that means that I have something like U transpose S times V is equal to F, something like this. And this S will be diagonal, so it's like S1, S2, S3, and V, let's see, U transpose like that. Let's see how do I write it in a good way. Yes, I can write like this. So maybe I write like this. So here each U here will be a kind of like the column vector of the U transpose here, and V here is a row vector of this V here. So it's like each V1, V2, V3 is the first row, second row, third row of V here, and U1, U2, U3 is the first column, second column, and the third column of U transpose here. So then this actually will be just expand to something like U1 times V1 times S1 plus S2 U2 V2 plus S3 U3 V3. So note that each of these is actually a rank matrix here, because U1 is a column vector times a row vector here will give you a 3 by 3 matrix here, and this also 3 by 3, this also 3 by 3. So if you sort this single value, so to be like this is maybe S1 bigger than S2, bigger than equal to S3, bigger than S3, you can have a low rank approximation by just discarding I mean, basically, this is f is exactly equal to this, but if you omit one of the terms here, then it will become a rank 2 approximation of this thing here. And of course, you want to approximate in the sense you will discard the one with the smallest single value. So in this case, you can approximate f using a lower rank matrix. And okay, I try to unshare here again. I don't know how I can do that. Okay. This sharing is very difficult. Okay, fine, let me get my screen back again. So actually that's it. Basically that's it. That's basically everything I have to talk about. Afterward, like you will just be able. I guess I was, for the time being, I will skip like a simple demo. I put it online. This is just like well, like maybe I will just show it anyway. So, but I won't want it now. So it's like just a very simple. Demo here, like with like two screen, two different view here, and I'm kind of just like copying code like from the OpenCV tutorial as well. Basically, we try to compute the some corresponding points, and then I use a OpenCV like built-in library to try to built-in function to try to estimate the fundamental matrix. And as you estimate the fundamental matrix, you can draw the epipolar lines and the epipole here. So I guess that's the end about like what I like to talk about here. But I just like have a quick summary of the entire course, and then also like actually a little bit advertisement of like. So you see, like we talk about like the whole course is about computer vision, but you see like all of these are very much relating or connecting to like classic signal processing and also like so-called AI. Like, but you see like really like people talking about okay, kind of like in science fiction is very much different from the real world. So in real world, like kind of technology wise, the really the three different three pillars of like AI. I guess many will consider that way. It's like really the symbolic model. There's something like expert system, and the second one is like graphical model like Bayesian techniques, and the third one is neural networks. And we kind of mentioned about neural networks in the last couple of weeks. And if you're interested, you can dig deeper like in my another class like explain. But the other one that for the second pillar, I say like for Bayesian graphical model will be coming up like immediately in fall. So the title is a little bit kind of like weird for historical reason, but it's really about like Bayesian graphical model. And what we look into there is like using probabilistic models to do inference. So basically just like try to how to build like your unknowns, like how to organize your unknown variables, like what your unknown things basically into a graphical model, and then trying to infer like knowledge from that, like from the observations, from what you see to infer like what you don't see, and also try to learn the structure of the model as well. So some of these applications like can be like predict, for example, stock market, like maybe like recommending system, like predict for Amazon like to recommend books and movies and so on, or doing some medical diagnosis, or maybe predict trend, maybe like for example for the virus, when are we going to end and stuff like that. And okay, that's the last slide. So like this a good time to end. Like, so hope to see you again in future classes, and like good luck with finals, and like have a nice summer break. And so I don't know. I received some emails like if some of you guys have questions, if the homework, like if you want to stay behind and like discuss the homework, is fine with me. So if not, then like or like if you have any other questions and so on, like you'd like to bring it up, is is a good time also.
Okay.
Yes.
I thank you. I have a question, and not about the homework.
Yes.
I don't know. Should I wait?
Oh, it's okay. Like you can talk about that. Yeah.
Okay, it's about kind of my project. So I've implemented a YOLO
Yes.
network
Yes.
to detect the dice. I don't know if you remember reading my
Yes.
proposal.
Yes.
Okay. And I've got it set up so that I can make predictions on individual images, but I kind of wanted to try to make a kind of a live application that could take like a video stream
Mm-hmm.
and run the predictions on frames. And I'm kind of having trouble starting. Like, where would I start looking at how to do that?
Actually, which library? Okay, you're using TensorFlow or like Darkflow or
I'm
using?
using TensorFlow, but I'm using the Keras API
Okay.
for it.
Uh, uh, but the tricky part is like, for example, YOLO, they have multiple implementation. You know, they have PyTorch. And for the
Yeah.
original offer, for example, Darkflow, I think you can from this from what they have already they can accept video streams basically. I remember like just let it
Oh,
run. You can yeah. So if you have trouble with TensorFlow and Keras, you may also check the I don't know what was the latest for like TensorFlow, but at the beginning, like the implementation for YOLO was not that great. Like it was a bit slow, and I think like Darkflow, like the original implementation by the authors is they claim to be like fastest. So if
okay.
you want to
The
try,
dark flow you said. I'll
yeah,
take a
yeah,
look at that.
Darkflow. So if you look for yeah, yeah, you but of course, like, he wrote his own library, something like that. So
Okay.
this will be only for that application, and it's not too uh, applicable like to other applications, basically. Uh,
Sure, but I've
yeah,
got a bunch of like
yeah, yeah. The lag will
animated
be horrible.
training
Like
data.
basically, yes, it won't be very fast. Are you using any GPUs?
Yeah.
Yes. But for Darkflow implementation, I think this actually can be made real time, close to
Okay.
real time. Yeah,
Cool. I'll take a look. Thank you.
yeah.